Hi, here are the quick answers for page 5 for you to check. So pause if you just want to check those. Otherwise, I'm going to go through full solutions for the rest of the video. Okay, so question 3 is a continuation of the elevator question. Now the elevator is getting to the top of the building and it's accelerating downwards. So for something that's moving upwards, and these are its velocity arrows, its acceleration when it slows down is downwards. So that's what it means to say it accelerates downwards. It's now slowing. So construct a force diagram for this picture. So if we know the acceleration is downwards, the total force also has to be downwards. So I'm going to have that in my mind as I draw my force diagram, because my force diagram has to total give this. So I've got my force of gravity. That doesn't change on passenger by Earth. And for this one and my normal force on passenger by floor, for these to total and give this downwards arrow, this one must be very small. Okay. If we go back and just think about these situations really quickly, you had 3 situations. You're going at a steady speed, and the normal force was the same as gravity. At the start of the elevator accelerates upwards. So you think about when you get in an elevator, when you accelerate upwards, you kind of feel heavy and your legs kind of buckle a little bit. That's because there's a big normal force pushing on you. That's why your legs feel like that. Gravity doesn't change, but this normal force you can feel. And when you get to the top and it slows down, the accelerator accelerates downwards, you kind of feel a little bit floaty. It's because your normal force is not as big. Right, so write an equation for the vertical forces on the passenger. I'm just going to be writing out these arrows, but as a formal equation. So my total force is given by, this time this one's bigger. And so if I subtract this one up the top, then I get my downwards one. There we go. So calculate the force the floor exerts on the passenger. I'm just going through the same thing. I can work out my total force, that one, by working out MA, which is 85 kgs times 3 meters a second squared. And I'll do that in my calculator. 255. And I'm after the force the floor exerts on the passenger, so I'm after this one here. So what I might do is I might add Fn to both sides. So then I get plus Fn equals Fg, and then I might subtract total force from both sides. So now I have Fn equals Fg minus total force. So I've got my total force now, 255. My force of gravity hasn't changed. It was 85 times 9.8 newtons a kg, which was 833. So 833 newtons minus 255 newtons, and that is 578 newtons. Cool. While descending in the elevator, the cable suddenly breaks. Oh dear. How big is the force on the passenger by the floor? Explain your answer. So what happens is that the cable breaks. And what happens? If we look at the system of the box now, or the elevator, the whole elevator, if we look at that, it used to have a tension force and a force of gravity. okay, depending on if it was accelerating or not, but it had this tension force on this rope. It no longer has that tension force. So the whole elevator just has this. So now the whole elevator only has that, so it's in free fall. Its acceleration is going to be 9.8 meters per second squared, and it's just going to fall. As soon as it starts falling, so a split second after it starts falling, the person will no longer be touching the ground because the elevator started falling downwards. And so as soon as it starts falling, let's think about the person. As soon as it starts falling, the person, if we do a force diagram, isn't touching anything, so it only has force of gravity on it. And so it starts falling as well. And they fall together. And so that's it. You don't hit the ceiling or anything like that. As soon as the elevator itself starts falling downwards, it moves away from you. You start accelerating downwards as well because there's nothing to push you upwards. And so you fall at that. So how big is the force on the passenger by the floor? There's no normal force at all. And it turns out when there's no normal force, you feel weightless. So this person's going to feel weightless all the way down until they crash into the ground at the bottom. So that was my explanation. Maybe I should write it. Cable breaks. And on elevator, total force is just gravity. It free falls. And it starts falling. Person falls with it. And as they are falling, they're not touching floor. So F of n equals 0. There it is. If you want to copy it down, just pause and copy it down. A 70 kg skydiver jumps out of an aeroplane. Immediately after jumping, how large is the skydiver's acceleration? Well, when the skydiver jumps out immediately, there's no air resistance. He's just started his fall. We draw our system. Is there anything touching? No air resistance at the moment because he's just started his fall. So at the moment, the only force is the force of gravity on skydiver by the Earth. So what's his total force? His total force is that. We know total force equals ma. So if we wanted to find A is total force divided by m, and we know the total force is the force of gravity over m. We know the force of gravity is mass times the gravitational field strength. So the acceleration is that, cancel them out, and we get the acceleration is g. Acceleration is 9.8. Upon reaching a downward velocity of 100 miles an hour, 300 newtons of drag resist the diver's motion. Draw a force diagram for the skydiver. So now the guy is going fast, and there's some air resistance. So now we've got our force of gravity on skydiver by Earth and our friction force on skydiver by air, and that's equal to 300. We've got a 70 kg skydiver, so the force of gravity is equal to 70 times 9.8 newtons per kg, which is 686. Right, what's the total force? 686 down, 300 up. It must be, subtract the 2. I get a total of 386 newtons downwards. I know total force equals mass times acceleration. So acceleration equals 386 386 newtons divided by mass, which is 386 newtons divided by 70 kgs, which equals 5.5 meters per second squared. And that's the end of that page.